was all very straightforward. I get an answer that was number 1. Okay, so the transform is just the sum of those two pieces, and the region is the region of overlap. The more interesting case, a more interesting case, and where things are a little bit different when we think about the bilateral Laplace transform than the unilateral, is that the regions can be more complicated. So here's an example where I've got a backwards traveling wave, a backwards traveling function. So now the function only exists for t less than 0. As you might expect, just stick it in the formula and see what happens. So stick this expression into here. Now it lops off the top of the integral. But when you're grinding through integrals, it's hard to tell the difference. You get something that looks very much the same. The thing that is different, notice that the function was upside down. It was minus something rather than plus something, like the first example was. So the first example was e to the minus t, t bigger than 0. This example is minus e to the minus t, t less than 0. That gave me a minus sign here, but the non-trivial limit is at the top rather than at the bottom. That's the reason I put the minus sign in, so it would kill the other minus sign. Also, since I need convergence at t equals minus infinity, the region flips. I still need to have that sort of a thing decay so that the integral exists, but now the functions are flipped in time. So the important value, the important range of S is now flipped. So now I get the same functional form exactly, but a region that's on the other side. That's one of the central differences between the bilateral and the unilateral transform. I need to tell you the region of convergence for you to know which of those two functions that I'm talking about. Okay, so the important thing from this example is the functional form looks exactly the same. I had a functional form in time, e to the minus t, e to the minus t. It was that functional form of time that I cranked through the integration for, and it's not surprising then that I get a functional form for the S transform that looks the same. If you start with functional forms in time that look the same, you get functional forms in S that look the same. However, since the region of t was different for the two functions, the region of S is different. There's also the negative sign. There's the fact that this flipped this way. And that's related to the fact that my region of integration extends from minus infinity to 0 versus 0 to infinity. The important limit flipped from being the bottom limit to the top limit. Okay, that's roughly it. So just to make sure that everybody's with me, what's the Laplace transform of this symmetric looking function? So which of those functions is the Laplace transform of the symmetric function? Right. It's about 3 calories to raise your hand, right? Good exercise, makes you breathe. The answer is, oh, come on. Okay, it's more like 90% correct. So not everybody has it right. What am I going to do? It's just like the last one, right? Just stick it in, right? If you think about writing the integral of this, the complicated part is this absolute value sign thing. So split it into 2 parts. That way, the absolute value is one thing when t is bigger than 0, and it's a different thing when t is less than 0. Now it looks like just the sum of 2 functions that are both trivial, right? One is right-sided, the other is left-sided, so we might be expecting something a little funky compared to the last one. So, so this guy that is left-sided in time ends up with a left-sided transform, just like the previous examples. So we see that this part, which looks like a pole at 1, so we're going to get a part of the transform that has a pole at 1, and it's going to be valid for regions in S space for S magnitude less than 1, okay? Then we're going to get this other piece, which comes from, it corresponds to a pole at -1, and it's right-sided, so like the right-sided examples that we saw before, there's a right-sided region of convergence here. So it's going to be right of its pole, but its pole is -1. So in sum, the region is going to be to the right of the pole at -1 and to the left of the pole at 1, because we have to be in the part of S space where both of those 2 integrals converged. So we end up with the ROC being the intersection. Okay? So we get a pole 0 pattern that looks like this. There are 2 poles now. When you add together a part that looks like a pole at -1 and a part that looks like a pole at 1, you get 2 poles. And the region becomes the band in between. Again, because the regions of S transforms, because of Euler's expression, is determined by the real part of S, so that we're always going to get some kind of a vertical band. The band's always going to be delimited by a pole, just like it was in a Z transform. There's 2 poles, so all we really need to worry about is which region bounded by 2 poles we're going to correspond to. Okay? So so the answer was 2. Written in a little bit of a funky form, but if you factor this, you can see that there's 2 poles, one at 1 and one at -1. Okay? So what I want to do, so hopefully that's all trivial, right? That's all stuff you can do in your sleep, right? What I want to do is think a little bit about what the implications are. What are we doing? What is a region of convergence? So I want to think